All right. It's funny when I've done that in the past, because what did I do? It was after class or something, and I still had the projector on. And I'm in here by myself and I'm recording. And when people would come to talk to me, and they're like, "Oh, are you recording a video?" And I say, "Yeah," and they do this because they think they'll be on camera. I thought that was funny. All right, so today we're going to solve homogeneous linear systems. And we're going to have a specific kind. We're going to have, and we're splitting 8.2 into three parts because of the different ways that we end up solving these things. Not different ways, but different possibilities. So today we're going to have distinct, real, something that we call eigenvalues. And we'll talk about what an eigenvalue is in just a minute. It's what our new math term for this unit. So last time in section 8.1, we verified that this e to the 4t is a solution to x prime equals this matrix 2, 2, 1, 3 x. So we verified that that was a solution. We can verify that negative 2, 1 e to the t is also a solution. So the general solution then is going to be x equals c1 times negative 2, 1 e to the t plus 1, 1 e to the 4t. So our question is, or what we wonder, is can we always find a solution to this kind of equation in the form of k e to the lambda t? Where k is a matrix, e to the lambda t, always a solution to this type of equation. Because this is similar to what we saw with our higher order differential equations, where we said, well, what if e to the mt is a solution? What does that imply? And that's how we came up with our auxiliary equation. So we wonder the same thing here. So in that case, if x prime equals ax, where A is an n by n matrix, and x equals k e to the lambda t is a solution, that tells us that k lambda e to the lambda t, that's x prime, equals a k e to the lambda t. This is ax. And we know that e to the lambda t is not 0. So we can divide by e to the lambda t, and we get a matrix equation. So a times k equals lambda times k. So we're just dividing this equation by e to the lambda t. A times K equals lambda times K. Or, I'm going to rewrite this, A K minus lambda K equals 0. And I'm going to simplify just a little bit further. And I'm going to say A minus lambda times the identity matrix times K equals 0. Factoring that column vector K out of there. So I'm multiplying the lambda by the identity, n by n identity matrix. Yes.
Why do you multiply lambda by the identity matrix but not n?
A is a 4 by 4 or n by n matrix already. Lambda is just a constant.
Oh.
So we multiply in order to factor out that K. We need a n by n matrix there. And this is equivalent to just as a set system of equations. We have A11 minus lambda times K1 plus A12 K2 plus dot 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 plus A1n Kn equals 0. And this is A21 K1, so I don't need parentheses there, plus A22 minus lambda times K2. The identity matrix has 1s on the diagonal and 0s everywhere else, plus dot 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 plus A2n Kn equals 0, and this goes all the way to An1 Kn and over to Ann minus lambda times Kn equals 0. So we have this system of equations here. So we need to solve this system. For our column matrix, column vector K. So K1, K2, K3, K to Kn. Well, in order to have solutions other than the trivial solution would be that all of our K's are 0. We need, if we take the determinant of both sides of this is an n by n 0 matrix, this is an n by n matrix, the determinant of the right-hand side is 0. So we have to have the determinant of the left-hand side be 0. And we don't want K to be 0. So in order to solve this, the determinant of this quantity has to be 0, because the determinant of this side is 0. So to have a non-trivial solution, we need the determinant of A minus lambda I to be 0. Well, that determinant gives us a polynomial in lambda. So we can solve that polynomial. We get lambda, whatever powers of lambda equals 0. So we can solve that polynomial for lambda. And then we can substitute that value of lambda into this system of equations. Because our a's are known, we can substitute lambda into this system of equations to solve for our K1, K2, K3, etc. This equation determinant of A minus lambda I equals 0 is the characteristic equation of the matrix A. And the solutions are what we call eigenvalues. Of A. So the characteristic equation is characteristic to the matrix A, and the eigenvalues are specific to the matrix A, because this equation only involves the matrix A. Eigenvalue, eigen is from the German, means characteristic, so the eigenvalues are the characteristic values, and sometimes you hear them referred to as characteristic values. And a solution for our vector k not equal to 0, that corresponds to a particular lambda, particular eigenvalue, is called an eigenvector. So we have the characteristic equation, the eigenvalues, and the eigenvectors of matrix A. And a solution to the system then is x equals k, that eigenvector that we found, e to the lambda t, where lambda is the eigenvalue that we find. And then for a two-variable system, we would find two eigenvectors, two eigenvalues and two eigenvectors. And then we would have our fundamental set of solutions. We can find our general solution. So the procedure that we're going to use to solve systems of differential equations is forming this determinant, solving that polynomial that we get for our values of lambda, for our eigenvalues, substitute those eigenvalues into this system of equations, solve for our eigenvector associated with that particular eigenvalue, and that gives us one of our solutions. Generally, for what we're going to do, the polynomials are generally easy to solve. And in general, these eigenvectors, the system of equations tends to be a pretty easy system of equations to solve for what we're going to do. All right, so solving systems of differential equations, kind of not really surprisingly, because it's a system, involves linear algebra. And this eigenvalues and eigenvectors, this is the most linear algebra stuff that we'll end up doing in this class. This is all the linear algebra you need to know for what we do. All right, so today we're going to work with the case where our eigenvalues are real and distinct. Because we know for solving a polynomial equation, we could get real distinct eigenvalues, we could get repeated eigenvalues, and we could get complex eigenvalues. So that's why we split I'm splitting this section in 3 sections. We'll talk about distinct real eigenvalues today, repeated eigenvalues tomorrow, and complex eigenvalues on block day. And then we'll start talking about non-homogeneous systems. So when an n by n matrix, n by n, A has n real distinct eigenvalues, lambda 1, lambda 2, up to lambda sub n. We can always find n linearly independent eigenvectors. And that will be vector k1, k2, up to k sub n. So when we have real distinct eigenvalues, we can always find linearly independent eigenvectors. And in that case, our fundamental set of solutions to our system is x1 equals k1 e to the lambda 1 t, x2 equals k2 e to the lambda 2 t, and we go up to xn equals kn e to the lambda nt. And this is on negative infinity to infinity. Because e to the lambda t, that's a nice function. Now when we have repeated eigenvalues, there's a little more work to find our linearly independent eigenvectors because we only have one eigenvalue to work with. And then with complex eigenvalues, the work is not finding the eigenvectors. The work is to represent our solution as real functions. There's just a little algebra involved there. All right, so questions before we do an example. So backing up, when we are solving these things, our goal is to we form this determinant from our system. We solve the polynomial, find that determinant, solve the polynomial for values of lambda. We use those values of lambda in this system of equations to solve for our eigenvectors, k1, k2, k sub n, to come up with a solution. Once you do the procedure a couple of times, it's very mechanical. So let's look at the example that we gave the solutions to before. So let's look at x prime equals 2, 2, 1, 3, x. So we need to find the eigenvalues and the eigenvectors. So we need to find the determinant. And I'm going to write this out explicitly here. 2, 2, 1, 3 minus lambda times our 2 by 2 identity matrix. We need that determinant to be 0. What I usually do is I say determinant, or I just do it this way, a minus lambda I. And I think about this in my head. So we're going to get 2 minus lambda, 2, 1, 3 minus lambda. And that's our determinant. 2 minus lambda, 2 minus 0, 1 minus 0, 3 minus lambda. So that becomes our polynomial. We get 2 minus lambda times 3 minus lambda when we make that determinant, minus 2 equals 0. And this becomes, when we multiply this out and simplify, this gives us lambda squared minus 5 lambda plus 4 equals 0. And this factors nicely. Lambda minus 4 lambda minus 1 equals 0. So this means lambda 1 equals 4, and lambda 2 equals 1. Those are our two eigenvalues. So for lambda equals 4, we need to find the eigenvector associated with lambda equals 4. So for lambda equals 4, we need to solve a minus lambda I times k, I'm going to say k1 equals 0. We need to find that eigenvector. So I'm going to write this out explicitly. This is 2, 2, 1, 3 minus 4, 0, 0, 4. That's lambda times the identity matrix. And we're multiplying that by the column vector k1, k2, and we need that to be 0. So this gives us our first row. We get 2 minus 4, which is negative 2. Negative 2 k1 plus 2, 2 minus 0 k2. Equals 0. And for the second row, we get 1 minus 0 times k1, so we get k1. 3 minus 4 is negative 1. Well, these are both the same equation, right? We need any eigenvector, any value of k1 and k2 that makes this true. So I'm just going to say from here, we have k1 equals k2. Any values of k1 and k2 that make this true is an eigenvector. Anything that we'll pick is any numbers that we pick that satisfy this are just going to be scalar that make an eigenvector that's a scalar multiple of another one. So pick the easiest numbers. So I'm going to let k1 equal k2 equal 1. So our solution associated with this eigenvalue, x1, is 1, 1. That's our column vector, e to the lambda t. And that's one of the solutions that we verified previously. For lambda equals 1, for lambda equals 1, what I usually do is I go to this determinant, because my equation is going to be 2 minus lambda times k1 plus 2 times k2, 1 times k1 plus 3 minus lambda k2. And I just put my lambda in there, and I think about that multiplication from here, so I can just write down my equations. So for lambda equals 1, we have k1 plus 2k2 equals 0. And again, k1 plus 2k2 equals 0. Because I get 2 minus 1 is 1 times k1 plus 2 k2. And here I have 1 k1. 3 minus 1 is 2 k2. Well, these are both the same. So I have k1 equals negative 2 k2. Any k1 and k2 that make this true is going to be an eigenvector. So I picked k1 equals 1. Or no, I picked k2 equals 1. So k1 equals negative 2. Well, we can pick any k1 and k2 that satisfies this equation. And it would still be a valid eigenvector, and it would still make a solution to our equation. So we get k2 equals 1, negative 2. And we can see that 1, 1 and 1, negative 2 are linearly independent because we can't multiply 1, 1 by a scalar and get 1, negative 2. They are linearly independent. So our x2, our second solution, is 1, negative 2, e to the t, e to the lambda t. And our general solution is x c1, 1, 1, e to the 4t, plus c2, 1, negative 2, e to the t. And if we wrote this out explicitly, not as a matrix equation, we were talking about x and y, this would be x equals c1 e to the 4t plus c2 e to the t, and y equals c1 e to the 4t plus or minus 2c2 e to the t. All right, questions on what we did there? So as we said in section 1, we can think of the two solutions. X equals c1 e to the 4t plus c2 e to the t, and y equals c1 e to the 4t minus 2c2 e to the t. We can think of those as parametric equations for x and y. And then we could graph that set of parametric equations in the xy plane and get a graph of a particular solution for a value of c1. So if we graph these in the xy plane, we call that the phase plane. A graph for a particular value of c1 and c2 is called a trajectory. And if we graph a bunch of values of the graphs for a bunch of values of c1 and c2, we get what we call a phase portrait. So let's look at, it's going to take me a second here because I haven't logged in. I want to look at a phase portrait for this equation. So let me freeze this and log in. Now what I'm going to suggest for what we're doing is if you have a 3x3 system, use some technology to help you out. Don't get bogged down in the details of either multiplying out the determinant for your 3x3 determinant, or for solving your third degree polynomial. Usually the 3 variable systems that you get for solving for your eigenvectors are pretty simple. So those are not too bad. But we'll look at a 3x3 system here in just a second. All right, and I'm almost there. All right, so for this widget, we're putting in our equations into equation 1 and equation 2. So so from what we had, let me go back. This is 2x plus 2y and 1x plus 3y. So that's what I'm putting in here. plus 3y. And I'm going to go from negative 4 to 4, just so we have a nice symmetric plot. And there is our phase portrait. So what we see in this phase portrait, this is for a bunch of values of our constant. So we have a bunch of trajectories there. The arrows indicate which direction, if we think of a particle moving, the particle would move as t increases. And the lines, these lines through the origin, correspond to our two eigenvectors. So our one eigenvector was 1, 1. So that corresponds to y equals x. And the other one, our second eigenvector, was 1, negative 2. So that's x equals negative 2y, or y equals negative 1/2 x. So that corresponds to this one. And actually, we kind of get 4 half lines because this goes this way and that way, same there. And we see that if we put a particle near the origin, the particle would always move away from the origin. And in this case, we'd call the origin a repeller. The origin is a repeller here. So the phase portrait gives you an indication of how your solutions are going to behave. And what the graphs of your solutions look like. All right, questions so far? All right, let's look at another example. All right, so we have x prime equals 1, 0, 1, 0, 1, 0, 1, 0, 1, x. Now this corresponds to, if I wrote this as equations, I would get dx dt equals x plus z, dy dt equals y, and dz dt equals x plus z. That would be the system of differential equations that this matrix equation corresponds to. So we need to find the eigenvalues. So we need to find the determinant of 1 minus lambda, 0, 1, 0, 1 minus lambda, 0, 1, 0, 1 minus lambda. And we need that to be 0. So when I multiply this out and simplify a little bit, I'm going to say algebra. We end up with negative lambda third plus 3 lambda squared minus 2 lambda, and that equals 0. And this is not a terrible equation. We get negative lambda times lambda minus 2 times lambda minus 1 equals 0 when we simplify. So we have 3 distinct eigenvalues: lambda equals 0, lambda equals 2, and lambda equals 1. So we have to find our eigenvectors associated with each of those eigenvalues. So big picture, we have a 3 by 3 determinant to determine. We have a third degree polynomial to solve. Then we have 3 by 3 systems of equations to solve for our eigenvectors for this system. Luckily, the 3 by 3 systems are nice. For lambda equals 0, we get, for lambda equals 0, I get 1, 0, 1, 0, 1, 0, 1, 0, 1, times k1, k2, k3, and we need that to be 0. That's a system of equations that we need to solve. Well, this corresponds to this first row. I'll write this out. Usually I would go straight from here to solve this, but I'm going to write this out. This gives us k1 plus 0, k2 plus k3 equals 0. That's from the first row. 0, k1 plus 1, k2 plus 0, k3 equals 0. 1, k1 plus 0, k2. That's the same as the first equation, plus k3 equals 0. Let me erase this one. Well, this tells us the first equation and the last equation tell us k1 plus k3 equals 0. And this the middle equation tells us the only way this is going to be true is if k2 is 0. That's the only way this second equation can be true. So k2 is 0, k1 plus k3 equals 0. So I'm going to let k1 equal 1, k2 equal 0, and k3 equal negative 1. So k1, our eigenvector, is 1, 0, negative 1. For lambda equals 1, our equation becomes, well, here we get 1 minus 1. So I get 0, 0, 1, 0, 0, 1, because this is 0, not 0, 0, 0, 0. Sorry. And I get 1, 0, 0 times k1, k2, k3, and that equals 0. So from this first equation, we get k1. I'm just going to read it directly from here. K1 has to be 0 because, or sorry, k3 has to be 0. I get 0 k1 plus 0 k2 plus k3 has to equal 0. So k3 has to equal 0 from that first row. From the last equation, I get k1 plus 0 k2 plus k0 k3 equals 0. So I get k1 has to be 0. And for this equation, I get 0 times k2 equals 0. K2 can take any value. From this middle row, I get 0 k1 plus 0 k2 plus 0 k3 equals 0. We already determined from this equation and this equation that k1 and k3 is 0. So the only way this equation will be true, no matter what value k2 has. So I'm going to let k2 equal 1. So k2 is 0, 1, 0. And we can see that these two are linearly independent. There's no way I can multiply either one of these by a constant and get the other. And then finally, for lambda equals 2, I get, well, here I have 1 minus 2. So I get a negative 1, 0, 1, 0, negative 1, 0, and 1, 0, negative 1. Times k1, k2, k3, that equals 0. From the first and the last row, negative k1 plus 0 k2 plus k3 equals 0. Same here, I get k1 plus 0 k2 minus k3 equals 0. I get k1 equals k3. And again, from this middle row, if I have 0 times whatever these are, minus 1 times K2, plus 0 times whatever this is, and that equals 0, K2 has to equal 0 from the middle row. So I'm going to let K1 equal K3 equals 1. So K3 column vector is going to be 1, 0, 1. And we can see that neither of these two can be scalar multiples. None of them can be scalar multiples of each other, so they are linearly independent. And the solution, finally, x equals C1, 1, 0, negative 1. This is e to the 0. That's our 0 eigenvalue. C2, 0, 1, 0. E to the t, that's for lambda equals 1, plus C3, 1, 0, 1, e to the 2t. Yes?
You said like usually we're not expected to do like a 3x3s by hand.
I mean, this one, I would not do this one by hand. I think this one is easier to do by hand than to do row operations or something. Personally, I think it would take me as long to put this in a calculator or type it into a whatever than to figure out that K2 has to be 0 and K1 equals negative K3. Same for this one. Same for this one. But if it's more complicated, usually the solving for the eigenvectors for a 3 by 3 matrix it's not that complicated. Usually. Sometimes you have to do row operations. The matrix A in this particular example is a specific kind of matrix. It's what we call a symmetric matrix. And a symmetric matrix is where A equals what we call A transpose. And that just means switch rows and columns. So the rows become the columns. So let's go back here to matrix A. If I take row 1 and turn it into column 1, 1, 0, 1, oh, I get 1, 0, 1. If I take the second row, 0, 1, 0, and turn that into the second column, 0, 1, 0. The third row, 1, 0, 1, turn that into the third column, 1, 0, 1. So A and A transpose are the same when we switch the rows and the columns. That's called the transpose of the matrix. It is always the case that if x prime equals ax for a symmetric matrix, we can always find n linearly independent eigenvalues. Sorry, eigenvectors. And then that lets us find our fundamental set of fundamental family and form our general solution. Now, it is not true that if the matrix is not symmetric, that we can find n linearly independent eigenvectors. It is possible to find independent eigenvectors for a not symmetric matrix, but for a symmetric matrix, we are guaranteed that we can. for a non-symmetric matrix, we're not necessarily guaranteed. All right, so what I'm going to suggest, I would suggest at least trying some of these problems before next time, a couple, because everything we do from here on out involves the same procedure. Finding the eigenvalues, solving for the eigenvectors, and then you have to do some other things from there. So we're doing that process, finding the eigenvalues, finding the eigenvectors, over and over. That's going to be what we're doing for the next for the basically rest of chapter 8, is finding eigenvalues and eigenvectors. Because when we solve non-homogeneous systems, first we have to solve the homogeneous system, and that involves finding the eigenvalues and the eigenvectors. But if you go through the process a couple of times, it starts to make sense and it becomes a little more mechanical. Oh, I just do this, I do this, and you start to see the process. There's a lot to it, but it's not complicated. Okay. And who would have thought that solving differential equations meant doing linear algebra?
Linear algebra seems so unthreatening though. Like linear, I really, like we learned about lines in like algebra 1. Algebra is relatively unthreatening.
Yeah, linear algebra is not,
Matrices.
it's not difficult. There's just a lot of stuff to do.
I want algebra.
And this is section 8.2. These are all just finding your eigenvalues, eigenvectors. I think number 16 is just an initial value problem where you solve for your constants. 53A, I think you're finding the phase portrait using that widget that I put on and looking at the phase portrait of one of the things. But it's kind of fun to look at the phase portraits of different differential equations to see how the solutions behave, I think.